Good evening. Welcome to the July meeting of the Baton Rouge Astronomical Society. Tonight's talk will be given by Dr. Matthew Penny, professor at LSU. Dr. Penny?
Thank you. So hello everyone. Sorry that my talk title is off on the black bar of the projector. I teach here, so I should have known about this and planned for it, but I didn't. I'm going to tell you, give you a big, broad overview of, thank you for the lights, of planet formation and how we get the ingredients for planet formation, how they were created in the universe, and then tie it into my own work, which last time I gave a talk here, I didn't give it here, it was in the middle of the pandemic, I gave it over Zoom, and so I'll give you a bit of an update on that project that I talked about in a bit more detail then. Let's get started. So I like to start with just kind of an overview of what things look like from our plates here on Earth. This is a picture, and all my credits are on the bottom of the screen. I tried to credit the people that create these pictures, but they're shining out the window at the moment. So this is a really nice picture of a project that I've seen on Astrophotography forum, which is to create a solar system portrait. And many of them you see, they blow them up to the kind of actual size or same relative size for the planets, but this one I like because it shows them how we see them. So the moon is huge, and then we have the rest of the planets in the solar system, even the giants, Jupiter and Saturn, are significantly smaller from our point of view. You have Uranus, Neptune, but are barely visible here. And then we also have the ISS. So this is showing one that I've seen from the internet. So if anyone has done one of these projects and has one of these pictures, let me know. I would like to include something local rather than someone literally anonymous in this case. The credit is anonymous username. This is how we see our solar system, and it's played a huge part in our understanding of how planets like the Earth that we've stood or sat on here today have formed, and the rest of the planets. But we can also apply that to planets around other stars as well, and that's where my research interest lies. There we go. So if we bring everything up to scale, we're starting to bring in some more information about the relative sizes of planets. So now here are the planets all scaled to the same physical scale. So big giant Jupiter and Saturn, small Earth, absolutely huge sun that doesn't fit on the screen. And then scaled on the bottom is not by size or size of the planets necessarily, but scaled by their orbit size. So the solar system is huge, and here on Earth, and the terrestrial planets are all packed into a small area. And so our knowledge of this has come from astronomical observations. We've watched how the planets move around the sky, and taken images that resolved them once telescopes were invented, or used our eyes before that. And so that allows you to build up a picture of basically the scales of the solar system, and it can give us some clues about how the solar system formed as well. So the big massive thank you. The big massive planets are kind of out in the far reaches of the solar system. The smaller terrestrial planets like Earth are all quite close in. And so from this picture, theorists have developed, starting from the 1800s, but accelerating over time, have developed models of how the solar system formed, and then applied those to extrasolar planets as well, and found that often those models broke when you tried to apply them to other systems. But still, it's a useful exercise, and you learn by trying to recreate everything that you're able to see. So this is the picture we now have of the solar system. Is the number of concentric orbits. There's the large planets. I've already covered this. So what I'm going to talk about is kind of we'll start with the understanding of how planetary systems form. Then we'll look into the ingredients, what is necessary for that formation to take place, and where those come from. So in particular from the Big Bang and from exploding stars. And then we'll get into my research question, which is how does the mix of elements, so things like oxygen, iron, hydrogen, how does that mix affect the planetary systems that you form? And I'm doing that with large surveys using large telescopes, both on the ground and in the future in space. Okay. So I'm going to start with, and throughout I'm using a lot of the new JWST graphic design and images that it's been producing over the last year. And they put together this nice kind of picture of how planets formed and compared it to a recipe, which I like. So they start off with, just like all good recipes, you start off with an ingredient list, and then it tells you how to take those ingredients and build a set of planets. So start off with 100 parts gas, so a lot of gas, and then include some rock dust, they name it, some ground ice, and then with some gravity you can form a planetary system. The one slight inaccuracy is this ground rock dust. It kind of suggests that it's been ground down. No, it's kind of built up from individual molecules. But the ground is more represents what you should imagine it being like, but not the process by how it got there. So you start off with a giant molecular cloud somewhere in the galaxy or another galaxy. So this is a cloud of cold gas that has that in terms of the galaxy and the gas within the galaxy is relatively dense. It's cold, so there's lots of dust around, lots of kind of molecules that can absorb light and help the cloud cool. And as that cloud cools, it has less kind of random motions within it. And so the gravity of the self-gravity of the cloud, so the attraction of each individual particle to the other particles in the cloud can overcome the internal motions of the gas and dust. And so the cloud will slowly come together and start to collapse. And where the cloud is densest, those areas will collapse fastest. And you end up creating a quite dense concentration of matter, which is mostly gas at that stage, and eventually will collapse down until it becomes a star. And so as it does this, before it becomes a true star and begins nuclear fusion in its core, it will be a protostar, so it'll be a ball of gas that kind of looks like a star, but isn't burning. It doesn't have nuclear reactions in its core, but it's hot and starting to glow. But there's still material falling towards it, still gas and dust falling towards it. And that gas and dust, as it falls in, it has to obey the laws of physics. And one of the more important ones is the conservation of angular momentum. And so if there's any kind of tiny amount of spin in the cloud, as that material falls in, it must conserve angular momentum. And just like as a skater going from with their arms outstretched spin slowly, and then as they bring their arms in, they start to spin faster. So too will the material that's falling towards the star. And this means that as it spins faster, it flattens out into a disk. And this is really important for forming planets because it concentrates a lot of the material and increases its density. So you get a disk of gas and dust, and the dust will tend to settle down into the very center of the disk. And then in those conditions, the dust will it will be orbiting the star mostly, but it has some random motion. It feels dragged from the gas. And so you'll get collisions between the dust particles. And occasionally those collisions, they'll bounce, the particles will bounce back and not do anything, but occasionally they'll stick together. And the dust at this stage is kind of like dust bunnies. It's kind of very fluffy, not very dense. But you know how dust bunnies, they kind of stick together. The same kind of thing goes on in the cloud. And so gradually you can build up material into something that looks like a dust bunny, and then if you get enough of that, it can kind of get denser and more pebble-like, and then those pebbles become rocks, become boulders, and you can build up to things called planetesimals, which are kind of very, asteroids are that kind of size of object and a bit bigger, up to kind of very small planets like dwarf planets like Pluto and such. They're kind of the larger end of planetesimal. Yes?
What kind of time frames are you talking here?
So, great question. Thank you for reminding me. So yeah, this is kind of the collapse takes kind of tens of thousands of years. The entire time frame for this picture is about up to 10 million years. So collapse of the star is pretty quick once it gets going, and then it takes a few million years for the planetary building blocks to build up. And so yeah, once you get planetesimals, then the planetesimals will start kind of knocking into each other. There's lots and lots of them. In models of the solar system, there's about 50 times the Earth's mass in the outer regions, which is now just kind of Pluto and such. There's lots of stuff that's going on in this disk, and lots of relatively large bodies that will interact gravitationally and occasionally collide. Yes.
Question, is the formation where it's just a blob of gas.
Yeah.
Is it natural progression that all blobs of gas are going to do that, or not necessarily?
No, not all globs of gas will do that.
So I don't understand the difference between planet formation like a nebula.
Yeah. So I'm really bad on this because I'm bad at kind of gas physics. But there's a stability criterion which determines whether you'll eventually have the collapse or not, and it depends on it depends on the temperature. So the higher the temperature, the more random motions there are, and the more likely it will just randomly kind of drift apart.
Okay.
It could be other forms of motion, like kind of interactions that cause that to happen. But yeah, generally you need something cold for gravity to take over, because gravity, although it kind of holds us to the Earth, it's incredibly weak. And so you need lots of matter to be able to provide any kind of significant force. And so if you have things moving around, which temperature is basically just a measure of how fast things are moving around if they're in a gas, you disrupt that gravitational collapse.
So that's where the stellar winds and all that come into play. Like from the formation and the collapse of other stars pushing through the gas.
Yeah, so I'm trying not to get into kind of star formation as well, but yes, often star formation is triggered by other events. So a supernova going off nearby can compress a piece of gas enough to kind of push it over that threshold. Sometimes, eventually, once you start forming enough stars close together, they'll emit enough light and stellar wind to destroy the cloud as well. Which I'm actually I've got some pictures, which I'll come back to that in a second. Okay, so yeah, you build planetesimals, they start to collide, and eventually you can build up the cores of planets. I'm particularly interested in gas giant planets because they need another stage of formation as well. So in addition to the rocky material that they form from in the beginning, they need to gather a bunch of gas as well. And so that can happen once the planet core becomes massive enough, it can gather an atmosphere around it. And if that atmosphere becomes massive enough that it's like more atmosphere than rock, and there's still gas around it, it will very quickly gather all the remaining gas in its orbital region until it and grow to a much larger size, like Jupiter or Saturn. Yes.
I'm not sure if you're going to get into that detail. I can't quite remember how it's described, but because of the mess of different elements, the rockier stuff forms on the inside, and the lighter elements are pushed back. I can't quite remember the mechanism going on.
Yeah, I'm going to come back to that, so it'll be in about 20 minutes. But we'll cover that and knowing that you're interested, I'll cover it in a bit more detail than I otherwise would. So yeah, I'm interested in how the gas giants form, so they need this extra process. And this, as I said, this all takes place within about 10 million years. That time limit is set by how long this disk of gas can stick around. In that 10 million years, the star turns on. It starts fusing hydrogen in its core. It starts releasing a lot more energy, and that light will blow away the gas and basically halt the planet formation at the stage of it, once it reaches that time limit, basically. And so that's a challenge. Recently, this has become less of a challenge. A few years ago, studies were saying it only had about 3 million years to do this. But a new one that came out last year, it's kind of reanalyzed all the data and found that the average lifetime is now about 10 million years, which is probably about enough time to not cause too much of a problem for gas giant formation. But it's still a relatively short amount of time. Okay. So yeah, I promised pictures. So this is, of course, the Orion Nebula. This is a region of where star formation has been going on, and where the stellar winds have kind of blown a hole in the surrounding molecular cloud, and basically halted star formation in that location. But the bit that I'm interested in is if you really zoom in on the nebula, and so I don't know, I should learn where exactly this is, but it's looking at a relative, like zooming way in. So this is probably an amateur picture. Is it? No, it's a space telescope, so it's probably a professional telescope taking this one, but over a wide field of view, and then JWST has zoomed in on a specific patch of the Orion Nebula, and it's seeing one of the young stars that has formed in the nebula, and surrounding it is this disk of gas and dust. And so this is exactly that protoplanetary disk that I was talking about. And it's always nice to have pictures of. The pictures are hard because they're very small. Like this is 300 times the size of the Earth's orbit, which at the distance of the Orion Nebula is a very small angular size. Yeah, so.
Does that have a name, that particular?
I'm sure it does, and I didn't put it on the credit. But yeah,
Orion 294606.
Yeah.
I did.
Oh, yes.
Yeah,
This screen is really hammering me, so thank you for that. So yeah, that's one picture from JWST. This is another set of pictures of protoplanetary disks. They don't look as much like pictures because they're taken with sub-millimeter telescopes, specifically the ALMA array in the Atacama Desert in Chile. And so this is a number of, I think, 66 basically radio telescopes, but looking at shorter wavelengths than most radio telescopes. That have millimeter wavelengths, that's why it's called, well, less than a millimeter wavelength, that's why it's called sub-millimeter. And so by combining the light from all these telescopes, and they can build up the resolution to image I can't both.
Yeah, I think.
So yeah, they combine the light from multiple telescopes to give the resolution of a telescope the size of their widest separation. And so at longer wavelengths, you need to spread them apart quite a lot, so over a few kilometers in this case, to give you the resolution to image these protoplanetary disks in a lot of detail. And so yeah, this is a number of protoplanetary disks imaged by this telescope, and you can, most of these are face-on as opposed to the edge-on one from JWST, and you can see lots of features in these disks, such as kind of rings and gaps and spiral arms, and so this is all evidence of ongoing planet formation going on in these disks. And the nice thing is, while these are the scale, I don't have scale bars on here, but the imaging is high enough resolution that at least in some of these, you should be able to watch them over time evolve. It won't be much evolution. This is probably tens to hundreds of astronomical units, so the orbital period is going to be measured in tens to hundreds of years, but it'll be enough to be able to start to see that motion in a reasonable amount of time.
So is each one of those a future solar system?
Yes.
And then the planets evolve from
Yes,
that? Okay.
yes. So I've not been keeping up as much as I should have on what the status of these kind of dark rings is. There's some debate over whether they are the gaps formed by giant planets, basically
Already in there.
cleaning up that gas in those rings. I think that that has been kind of not necessarily disproven, but there's an argument that it's actually just a kind of feature of the way that the telescope's image. They're usually using a relatively narrow wavelength range and looking for emission from certain molecules, and the conditions of those rings is just prevents them from being as bright as the rest of the disk.
Is that why that one is a dark core rather than a bright core?
So that is, I don't know for certain. I would guess that it's harder to create a condition. So if you're creating a condition for a narrow ring in some of them, I would think it's probably harder to do that over a wider range. So this might be completely cleared out, but I'd have to go up and go and look, or you can do the same. But yeah. And then so most of these are from Alma. I guess this one. So I should be careful. So nearly all of them are Alma, but 2 of these are from Sphere, which is a near-infrared instrument. And so this is imaged in a different way
Okay.
from these. So that might be the
That's why.
explanation.
It's not that there's nothing there, it's just not that wavelength.
Yes, so Sphere is more like an optical telescope, and it has a coronagraph, so it blocks out the light from the star. And so that's probably what's causing it. So you can kind of see it more in more detail here. They haven't completely subtracted the star out on this one. And you're left with a bunch of residuals. Okay, and then so I've shown you two separate kind of 2D images, and I wanted to give you a sense of the 3D nature of these protoplanetary disks. So this is kind of this tilted kind of not fully edge on and not fully face on, and so you can kind of see that they look kind of well, this kind of yo-yo is the best sense that I can give you. So the edges flare up. They become pretty thick in the outer regions. And then you have this band of dust. Unlike the yo-yo, it's not a narrowing, it's light that's being blocked. So it's thickest and densest in where it's dark. But that's,
Okay, so it's not a void space, it's just different.
there's more material in the light isn't escaping. So this is all reflected light. So the star is in the center, it's shining out, it's hitting the disk, and then coming towards us. And so the light can't penetrate through the dusty disk.
Is that corresponding to the collapse of all the material as it spins around the protostar?
Yeah, that's contributing to it. Yeah, the closer in it is, the faster it's moving, the more angular momentum it has.
But just collapsing all the material, most of the material into the same plane, so to speak.
Yeah. Sorry, yes. To be able to get closer in, it has to shed angular momentum, which means it has to become more disk-like. And then there's more, closer in, it's denser as well. There's more friction that kind of dissipates that angular momentum.
So you have mostly dust in the middle and the gas on the outside.
Yeah, so there's a dust disk that's very thin, and then the gas disk is thicker. So in the very center, I think it's still more gas than dust by unit volume, but the proportion of dust is higher.
And over time, will that collapse on itself into a thinner disk at some point?
So I believe that as the star turns on, it starts boiling away the material from the upper disk edge, and then it kind of goes off backwards.
But not so much collapse and blow itself apart, blow that part away.
Yes, yeah. And so, yeah, you're left with the the stuff that stays around longest is the dust, which is heavier than the gas. And so you get a dusty disk for a while. I think that's about 50 million years that will stick around, but eventually that dust will also get blown away by radiation pressure. And so it's interesting that we do see some stars that are older than that with dusty disks, and that kind of is used to infer the fact that the occurrence of like a collision in the system to create a whole bunch of new dust. So yeah, it's kind of taken as evidence of planetary collisions, or at least asteroid collisions. Okay. My battery is running out. Okay. Well, my computer's being slow. So yeah, that's kind of the basic picture. In the solar system, we have a more complicated picture. That's because we have a lot more information to go on. So there's evidence from moon rocks, meteorites, and basically we can see pretty much everything that has been left over from the planet formation process. So not just the large planets, not just the small planets. We can see asteroids, all sorts. We can take measurements of them regularly. We can take spectroscopy of most of, or a lot of them. So we can take a spectra of individual asteroids, planets, etc. So we can build up a much more detailed picture, which needs a much more detailed model to be able to explain everything that we see. And most models still struggle to explain everything. But the basic timeline we have is that so 4.6 billion years ago, the sun forms, and it starts to form. The sun itself starts to form, and then the disk of gas and dust also forms at the same time. Over the next 10 million years, the giant planets form, as well as the rocks and things that form the asteroids, etc. And in that time, the sun ignites as well. But the weird part about the solar system is that it seems like the terrestrial planets, including the Earth, didn't form at that time, but formed later in the second kind of era of planet formation. And so basically what we think is that over the 5 to 50 million year time scale, we have a lot of gas giant planets in our system, two Jupiter and Saturn, and then Uranus and Neptune, and then possibly a fifth one as well. That's a hostile environment for small planets. And so it's thought that maybe there was something in the inner solar system before that time, but the interactions with the larger giant planets outside caused the destruction or ejection of anything that formed in the inner solar system, leaving a bunch of debris. And then over a longer time period, that debris could kind of recoalesce through collisions and the stirring impact of the outer planets into the small terrestrial planets, the 4 planets that we have here. And in particular, that would help explain why Mars is small. Normally, you would expect the size of the planets to grow as you move outwards, but if Jupiter is kind of disrupting its formation, then Mars being small makes some kind of sense. And so, yeah, that probably took 50 to 100 million years for that for the terrestrial planets to form. And along the way, there were, I don't know whether that video is going to play or not. It's going to spot my, no.
Okay, Lord.
Switch out that. Oh, but it is. Anyway. I'm not gonna. I'll skip the videos and not watch my life. So yeah, we can maybe play them after, and then if people want me to go back. So yeah, the solar system, the picture of solar system formation is more complicated because we have more data to kind of work out the kinks in the model and trying to understand all the different processes. And we think that the same kind of processes will go on in other planetary systems, just we're unlikely to be able to observe them in enough detail. Most of them, we can't see all of the planets in the system, we can only see a few of them. if using any given technique. So we're not going to build up the same kind of picture, but by combining our knowledge of this one system we can study in detail with the knowledge of thousands of systems that we can study in part, we can build up hopefully a kind of a universal picture of what goes on when planets form and then later evolve. And just completing the timeline, so after the terrestrial planets had formed, maybe there was a period of instability in the gas giant planets that maybe led to an ejection of one, like the fifth gas giant planet, potentially caused the late heavy bombardment, so all the cratering on the moon and Mercury and such. And then after 800 to 1 billion years, life on Earth began. So the questions that we're trying to answer in studying planet formation is also setting the stage for questions about does life form on other planets, so what are the conditions for that? And again, if you need certain mixes of elements, does that impact life, the occurrence of life elsewhere? Okay, pressing the button. Okay.
There you go.
Oh, there we go. I'm not going to try and bring back whatever just disappeared. So, getting back to the ingredients. So I've explained the process. What do we need to go into it? So this is like the ingredient list or the shopping list. And so we've got 100 parts gas, 1 part rock, 1 part ice. And so what does that actually correspond to? So for this, we need to go into chemistry a little bit, or not much chemistry, just a periodic table. And so this is the new astronomer's periodic table. It used to be, the astronomer's periodic table used to just have hydrogen, helium, and then everything else was just a metal. But nowadays we're a bit more nuanced. We have more spectroscopic instruments and more advanced analysis techniques that allow us to measure the abundance of various different elements, and lots of them in stars, and kind of do this on a mass scale. So there's big spectroscopic surveys that survey tens of thousands, millions of stars, and measure how much of each element there is in any given in each of those stars. And so now we have a good understanding of what goes into the stars and where they come from. And it turns out that pretty much everything that we're made up of, all the Earth around us, is made up of materials that weren't there originally. So, and by originally, I mean created in the Big Bang. So the Big Bang occurred, the universe was created, and it mostly, the elements that were created at that time was mostly hydrogen and helium, and then a tiny amount of kind of lithium and a few slightly heavier elements. But very little in the way of diversity of kind of chemical elements. The rest had to be created in the cores of stars or in explosive processes in the universe. So either they're released from dying low mass stars, that's the green elements, so carbon and nitrogen are particularly important ones of those. Exploding massive stars are colored in yellow, so oxygen is mostly created in exploding massive stars. And then we've got the purple and this kind of silver. Those are created in explosive processes. So either the merger of two neutron stars that leads to an explosion, for the purple, kind of very heavy elements, very rare elements, or for the silver ones, which includes some common stuff like iron, that has come from exploding white dwarfs. And then there's a few elements that have had to be created in a lab because they maybe get produced in these conditions, but they are unstable and decay to other things before we ever have a chance to see them. Technetium is actually an interesting case. It's observed in stars, and so in certain cases, and so that implies that it is created in astrophysical processes, but it has a very short half-life of a few million years, so it has to be continually replenished to be able to observe it. So yeah, that's where most of the elements come from. Last one, cosmic rays, just creates a few special elements here, beryllium and boron. Okay, so that's where everything is coming from. But linking this back to planet formation, so we get an ingredient list for not just, I think I'm going to stand by the computer and then I can actually change things. So, sorry for those online, I'm just going to send it back to you so I can see my screen. So for what goes into the sun, we have mostly hydrogen and helium. It's a star, made mostly of gas. But there is kind of trace amounts up to 1% of oxygen, carbon, iron, elements like that. And so these come from a mix of different places, but low mass stars produce some of it. Dying high mass stars produce the rest, and then the white dwarfs produce some of it. And we need a similar shopping list for the Earth. But this time we're limited to 2 different sources now, mostly. So most of the Earth by mass, 99%, has been created in exploding massive stars. So things like oxygen, most of the silicon, and then exploding white dwarfs have produced most of the iron and nickel, and that those kinds of heavier elements.
So those elements came from other solar systems, other stars
Yeah.
exploding and then get trapped into our system.
Yes, yeah.
It wasn't created within our system.
They were
Just trapped in our
formed inside other stars, kind of drip. The exploded material drifts away. Exploded material drifts away out into the kind of interstellar medium, so there's gas surrounding all the stars. And then eventually some of that will find its way into a giant molecular cloud, and the process starts again.
Dr. Penny,
Yes.
is there any statistical way that we've come from 10 recycled events, 20 recycled events? Is there any way, how many neutron, collisions have we come from? How many?
Yeah.
Is there any way to determine all that?
Probably not, but
Maybe never.
so I will. I'll come back to that in a second. But yeah, we probably can't count it, but we get a sense of the time for this.
Okay.
Okay, and then in addition to Earth, we're here, we're living. There's a slightly different shopping list again, a longer one. So by mass, we're made up of hydrogen. 99% is just 6 elements: hydrogen, carbon, nitrogen, oxygen, sulfur, and phosphorus. But then for a number of important biological processes, we need some rare elements like iodine, selenium, things like that. And that has come from these merging neutron stars. Okay, so where did each of these come from? Now, this is working again, so I'm going to step back and hopefully it'll just behave. And I'll just move closer if I need to. So yeah, this was the beginning. So this is the Big Bang. This is pretty much a picture of what the Big Bang looked like after 380,000 years. So this was an image taken by the Planck satellite. This is not the image they normally show. It's too boring. But the entire universe was basically, the conditions in the entire universe were about the same as the conditions at the surface of a low mass star. So a bit cooler than the surface of the sun, but kind of very star-like, a few thousand Kelvin, glowing in visible light of about this color. This is the average color of the universe at that time. What Planck observes, though, is not visible light. It observes microwaves. So over time, the universe expanded, and that light that filled the universe has continued filling the universe. It still does, but it's been stretched out, and the wavelength of it has gone from being nanometers to give you visible light to now microwave wavelengths, which is centimeters. the universe has expanded, don't have the number, but a few thousand times to give us now radio waves.
There you go.
And so now this is the picture that actually gets shown, which is showing the small changes in contrast over the entire universe. So the universe was extremely uniform, but there were small over and under densities in gas that basically became the seeds of galaxy clusters and that collapsed into all the structure that we see today in our optical light images from stars that actually exist now or in the recent past. And so the Big Bang happened, formed mostly just hydrogen and helium. Then those density fluctuations collapsed down, or the dense ones did collapse down, formed galaxies, and those galaxies then formed stars as well. And that formation of stars is what's needed to create the rest of the elements that we need for the planet formation process. And so the first stars appeared probably 200 to 400 years after 200 to 400 million years after the Big Bang. This number is getting revised by the recent JWST observations. I'm not super up to date with this, but they seem to be pushing that number a bit earlier, probably to the earlier range of this 200, but it's causing a lot of excitement in the galaxy formation part of the astronomy community. But over that time, all those elements will get produced in stars. And it turns out that it's going to be important what kind of star or what kind of explosion happens to build up the different mix that we.
Every single time you look at
Yeah. Every time I wait, it doesn't move on. But okay, and so yeah, as I can't remember who mentioned it, but the material that explodes, so the elements that get created in exploding stars, they get recycled back into the interstellar medium, and through generations of this, so multiple generations over time, you can build up the current composition of the sun, which has taken the elements of lots of different exploding stars to make up its exact mix. And so this is kind of a very old diagram at this point of the star formation cycle. You have a slightly different cycle for low mass stars to high mass stars. So low mass stars, of which the sun is one of them, they live kind of relatively quiet, long-lived lives. So they burn their fuel slowly. They live for billions of years, tens of billions of years, but eventually they use up all their fuel, become a red giant, and after some more complicated evolution, they will slowly shed off their outer layers and become planetary nebulae. In those planetary nebulae, they send off some of those elements that they created in the core. Some of them get mixed out of the core through convection, and so carbon and nitrogen gets released in this way. But most of them they will fuse carbon and nitrogen into oxygen, but that oxygen will remain in its core. And the core that's left is the white dwarf. And so if nothing happens to that white dwarf, that oxygen is kind of locked away forever. It's not going anywhere. The carbon and nitrogen will get cycled back into gas and form a new generation of stars eventually. But that's how the carbon and nitrogen get to us. The oxygen comes from the massive star route. So you form a more massive star that lives a shorter, more energetic life. It burns through its fuel much more quickly. After only a few million years, it will explode. And this time, rather than just leaving behind a white dwarf, it will leave behind a neutron star core. But before it does, it will have fused heavier elements, so oxygen, all the way up to iron. And the explosion of the core will spread all of those elements except iron. Iron gets destroyed throughout the universe or throughout the galaxy. And so this is where we get the oxygen, neon, etc. We do get a neutron star left over, so there is some remnant, but we'll lock away some stuff, but the process will produce the kind of heavier but not so heavy elements that we need. Okay, and so the time scales are really important for this. So it only takes a few million years to produce oxygen, neon, etc. It takes billions of years to produce carbon and nitrogen. So during the first stages, the earliest part of the universe, in the beginning there was just hydrogen and helium, pretty much. Then after a few million years of stars forming, you now had oxygen and neon around, but you had to wait a few billion years for significant amounts of carbon and nitrogen to show up. I described the process of kind of so massive stars, they build up individual elements in shells, and it's the shells that get ejected in the explosion. The core gets either destroyed and becomes a black hole, or it stays as a neutron star. Okay, so this is this here on my right. Yes, you're right. Is a picture of one of these supernova explosions. Actually, this is a picture of this is a white dwarf explosion. Sorry, I should be more specific about that. Taken from the 20-inch up here.
Okay.
Yes. Yeah.
Okay, I like this.
So it doesn't look as impressive, but that's because I'm trying to make a point. And so this here is a different supernova explosion with a lot of nice image processing to bring out the galaxy as well, but it occurred in. But the trouble is, if you bring out the details of the galaxy, you kind of de-emphasize how bright the supernova is. So this is a supernova here, this bright star-looking thing. It's actually outshining the galaxy. Because you have to apply a strong stretch to the galaxy to see its details, it kind of de-emphasizes the supernova. Here I'm just showing kind of a linear stretch, so the total amount of light. And so the supernova here is outshining the rest of the galaxy. They're incredibly bright events, and I feel like we don't get a sense for that when we see these pretty pictures of the supernova.
That's a type 1A.
This is a type 1A, yes.
Okay.
Yeah. So these are more luminous than the collapse of massive stars, but even those are kind of pretty much comparable to the luminosity of the galaxy. So yeah, that was taken by two LSU grad students. Reverting back to where I was before. So yeah, the other types of explosion we can get is exploding white dwarfs. For this to happen, you have to pile material onto a white dwarf. You can do that by kind of gravitationally attracting the material from a companion star. If it's let's say a giant star that becomes too big, some of the atmosphere of the giant star will come too close to the white dwarf and be attracted and fall onto it. And if you build up enough material in that way, you can get the white dwarf to explode. Or the other option is to just have two white dwarfs and have them come together and collide, and that will push you definitely over the limit that you need to hold the star together. And again, that will explode. It seems like most white dwarf explosions are actually the second type of the two merging white dwarfs. It turns out it's quite hard to set up the conditions for single white dwarf and giant star to actually build up enough mass, because occasionally they'll undergo novae explosions, which aren't destructive, but they will blow away some of the material it's been gathering. So yeah, that's how you get white dwarfs to explode. And just like white dwarfs can kind of spiral in together, so the in-spiral happens first. They kind of go through a common envelope phase where the white dwarf is orbiting inside the giant star at some point, but once that kind of brings them together, and then over time they'll emit gravitational waves that will slowly bring them together and then bring them to coalescence and merger and explosion. A similar process happens with binary neutron stars, which are just the remnants of more massive stars. And this was, of course, observed with LIGO recently. So this is a LIGO kind of gravitational wave event for a neutron star. It takes quite a long time because it's a smaller system than the black holes that we take as well. So yeah, these are how those explode. Okay, so when those explosions happen, they're energetic events. They're extreme physical conditions. They produce a lot of the heavier elements that aren't produced by either the massive stars exploding or by low mass stars. And so they will return those elements to the gas of the galaxy, maybe blow holes in the gas inside the galaxy. This is another JWST picture. And on the edges of these holes, you see maybe an overabundance of H2 regions when star formation is going on. So again, these explosions can help to trigger more star formation. Yes?
Is there a difference of opinion now about Betelgeuse, about the time frame for the?
You should ask Manos to come out. He has just published a review on it, so I haven't read the review yet. So I will decline to say anything.
Okay.
Yeah, I've not been keeping up with it as much as I should. Sorry. Okay, and so yeah, zooming in on these star formation regions, then yeah, this is I think this is a torrential nebula. Yes. In this large map.
LMC.
I should know this.
It doesn't matter, it's to the south of us.
Yeah, that's why I don't know. But yeah, you form new clusters of stars. New stars form from these kind of this cycle. I just wanted to show good JWST pictures of this.
Almost.
Oh.
Thanks, Steph.
Okay, so now we're back at this protoplanetary disk, and so we've gone through the life cycle, we've gone through the history of the universe, and we're back to now having stars forming from material. Those stars are now enriched with all the different elements, and if you get the element mix right, you can form something like the solar system. But my research interest is what if you change that element mix up? Like if you're baking, you should probably follow the recipe very closely to get the right result. But if you're making a stir fry, it doesn't really matter what you throw into the wok. You'll still get something that tastes good in the end. So yeah, I'm interested in what happens if you change the ingredient list up. Do you get different kinds of planets? Do you form more or less planets of certain types? And it turns out that's actually a pretty hard question to answer. So what we do know is that if you increase the total amount of non-hydrogen and helium, so astronomers' metals, usually traced by iron, if you increase the amount of iron, you will increase the number of giant stars that you produce. So if a star has a higher abundance of iron, so more of its mass is iron, then it will tend to have more planets. But it's a pretty strong effect. So here on this graph is the stars with the same amount of iron as the sun, and then if you double the amount of iron, you get more than double the number of giant planets. And so this makes sense to some extent. Like the more material you have, the more planets you can produce from it. But if you think about what makes up a giant planet like Jupiter, they're mostly hydrogen and helium. So why should the amount of iron really affect how many Jupiters you can form? And this comes from the start of what we were talking about. You need to form a core first, probably. So this graph is taken as strong evidence that the way that a planet forms is by forming first a rocky core or an icy core, and then gathering the massive envelope that Jupiter and Saturn have around them at a later stage. That's as opposed to kind of the planets just directly collapsing from the disk. And so yeah, this is taken as strong evidence for this core accretion scenario. So form a core first, and then accrete the gas onto it.
Now, that chart, is that a simulation, or is that an actual
No,
compilation of the known exoplanets?
Yeah, it's a pretty old one at this stage. This was very early on.
I see that.
2005, which is
Okay.
only 10 years after the first exoplanets were formed.
Has it ever been updated?
Yeah, so people have redone this kind of study on different kinds of planets and actually find different results for different types of planets. But yeah, for giant planets, it turns out that you get a strong correlation between the amount of metals and the number of giant planets you have. For smaller planets, it's actually less strong, which is kind of the opposite of what you'd expect to get. But
So Dr. Penny, Jupiter,
yes,
it's confirmed, Jupiter has an iron core.
sorry, I'm no. We actually don't know very much about Jupiter's core at all. We know that there must be more heavy elements in the core than there are in the atmosphere. The atmosphere is just very trace amounts, kind of similar to the sun, slightly more metals than the sun, but not by much. And again, I haven't kept track of this, but there's a mission called, why am I forgetting the name of it?
Juno?
Juno, thank you, yes. That is basically has sensitive gravity measures. So it can measure the differential amount of gravity as it orbits. Thank you for the pronunciation. And so by measuring that, it can kind of measure the shape of Jupiter's gravitational field. But it can only, like if it's spherical, it won't notice anything. So it's only noticing kind of small
A
departures.
few spots that have more density to it.
Yeah, but so this is far from my field of expertise.
So when you're saying more planets or giant planets, they're not all on these exoplanets, they're not all gas planets, correct?
That's right.
That must
So
be what I
yeah,
was confused on. Okay.
okay, yeah, I'll come back to that in a second. 2 or 3 slides. So yeah, more metals, you get more planets. But what I'm interested in is what metals are important. So is it the iron that's driving this correlation, or is it something else? And so
Is that coming from the light in the star, the concentration of iron?
the measurements of it, yes. Yeah, so people measure spectra, so split light into a rainbow and see absorption lines of iron. Is that the question you were asking?
Yes.
Yeah.
So your question is, yes, there's evidence there's iron there, but was that the initiating event, or was that just coincidental?
Yes, exactly. So the reason why I think that it might be coincidental is, so if we go back to our own solar system, we see all the giant planets kind of out in the outer regions of the solar system. And so this kind of observation has led to the belief, and well, not belief, but models that try and kind of recreate the solar system. And to be able to do that, they believe that you can't necessarily form giant planets in the inner part of a protoplanetary disk. There's less material there generally, and in particular, there's less solid material. So you can, and this is going back to one of the early questions, so you can, the inner part of the protoplanetary disk is hot, and so you could, to have solid material, only things like rock that don't evaporate are able to exist in the inner part. But if you get far enough out, the temperature in the disk is cool enough that you can start to form ices as well. So things like water ice, carbon monoxide ice, things like that. Water is H2O, carbon monoxide is oxygen, includes oxygen as well. And so this is why I think that the amount of oxygen is going to be the important element for determining giant planet occurrence rates, not the amount of
So does that mean that the gas planets that have been discovered orbiting their stars in a closer orbit than our own gas giants would be more likely to be pulled in by the gravity of their star?
Yes, yeah. So the first giant planets that were found very close to their stars, and that's actually what I'm looking for at the moment. But yes, it's believed that as they formed within a disk of gas, and so the gas disk applies a torque to them as they orbit after they've formed, and pulls them in towards the star. It's important to remember that only about 1% of giant planets known are actually very close to their stars. They're the first things we found because they're the easiest to find, but they're only a small fraction, so they're a rare case. But they're pretty obvious, and they're easiest to search for. So they kind of dominated our thinking for a while. But yeah, that's a good point. Thank you for bringing that up. Yeah, so I think that because, so basically you get more solid material out in the outer region because you have a mix of rock and ice. That is thought to lead to an increase in, basically gives you enough density of solid materials to form the core. And then that core, if it forms quick enough, can gather the gas around it. And so yeah, it's thought that only in the outer regions can giant planets form. Yeah.
So then angular motion plays a role in that
Yes.
process then?
Is there a question or is that?
No, I'm just verifying
confirm?
it.
Yeah. Yeah, so I think that rather than iron being the important element, I think oxygen is going to be the important element. So that's a hypothesis, right? We can go out and test it if we're good scientists. And it turns out that no one has really done this very well because it's very hard to do.
You're going to be the first.
No, as always with good ideas that you have, you find out that someone else has had it before you. But,
There's nothing new under the sun.
no, or above it. But yes,
Or in it.
yeah. But yeah, so other people have thought about this, but at the time they had limited samples of planets to work with, and so what they found was suggestive, but it's not really firm proof yet. So the reason why I was talking about exploding stars and timelines for that is because it turns out that the rate at which you form stars will set the mix of elements that you have in your star. So massive stars explode very quickly, so you very quickly build up oxygen. And so so what I'm showing here is a graph of, on the x-axis is the amount of oxygen in a star or in stars, and on the y-axis it's the ratio of iron to oxygen. So if you form your stars very quickly after the Big Bang, say in a globular cluster, they form very quickly in a burst. Actually, I take that back, but we can go into the details of that in a second. But if you form your stars very quickly, you do so mostly with just oxygen. You don't allow enough time for iron to form because the iron has to go through being a low mass star and then having those low mass stars interact with another star in some way, either a collision of a white dwarf or accreting material from another star for the white dwarf to explode. So it takes a while for any iron to form. And so if you form your stars very quickly, you can create a lot of oxygen very quickly and recycle that over and over again and build up the amount of oxygen in the next generation of stars that comes only a few million years after. But you'll be left without much iron. And so very old populations of stars don't have much iron, but they do have reasonable amounts of oxygen. And so globular clusters are an example of this. They do probably form in one relatively short burst, but they do have, so they don't have much iron, but they do have reasonable amounts of oxygen. And so, yeah, we can go into the details of globular clusters if we want, but I'm going to move on.
That's the population 2 stars, right?
Yes, yeah, so, yeah. The very earliest stars were probably slightly different, more massive. They would have produced oxygen in large quantities and So yeah, that's where the oxygen for globular clusters has probably come from. So that's forming stars in a quick burst very, very early on. But if you take more time to form your stellar population, so rather than a quick burst, but over 1 billion years, 2 billion years, something like that, then you might, which one am I looking at here? Yeah, this red line. So then you would still build up quite a lot of oxygen before you built up any iron, but the slightly older ones will start to build up some iron. But if you form your stars very slowly, so over the entire age of the universe, the very oldest ones in that population won't have much iron, but as you keep on going, you'll fold in more and more iron into them. And so you'll get a higher ratio of iron. And eventually you'll kind of saturate this increase, but you get different ratios of iron for the same amount of oxygen, depending on how long it took for the stellar population to form. And so this presents both an opportunity and a challenge. The challenge is that we live in the disk of the Milky Way galaxy, which basically follows this blue track. And it means that the amount of iron in Milky Way stars is just correlated with the oxygen. It's a very, very tight correlation. And so that correlation that we see in giant planet occurrence rates being with iron, it could just as well be due to oxygen. We have no way to disentangle. So to be able to disentangle whether it was iron or oxygen, we need to observe planet occurrence rates in other populations as well. And so then the problem is that the other populations of stars are a long way away, or are very kind of sparse. So there's the thick disk of the Milky Way, which is older. That's more like this red line. That we are embedded within the thick disk, so there are thick disk stars around us, but they're only like 1 in 100 stars, so they're in the solar neighborhood. So that's hard to measure planet occurrence rates around those. And then the globular cluster stars, they're a lot further away, and so they're a lot harder to search for planets.
There you go.
So yeah, this is a picture of the galaxy. Sorry, an artist's impression of our Milky Way. Is perhaps my favorite galaxy other than the Milky Way, but just I feel looks pretty much like it. It's got a bar. It's got a blue disk, and so you can see that just from the color of these different components, the stellar populations have different ages, and therefore different star formation history. And so this gives us a clue of where we need to look to search for different populations. So the center of the galaxy, the galactic bulge, formed over a much shorter period of time, but over a sustained burst. And so that has a population, a chemical enrichment pattern that's more like this blue line. And then we've also got globular clusters, which I mentioned. They form very quickly, and they have I'm confusing myself. But if we look at different populations, they have these different chemical abundance patterns. It's the one I'm trying to make. And so what I'm trying to do is look in these different populations of stars for these try and measure the occurrence rates of different planets. And so I'm going to just focus on the one search rather than going to the other. Sorry about this. So yeah, the survey that I'm conducting at the moment is using the 4-meter Blanco telescope in Chile. So this is since 2012. There's a really very nice wide field camera on it, but so normally imaging cameras have a single sensor. This has 60 of them, and it covers 3 square degrees. And so we use that to monitor about 6 million stars in the galactic bulge. We take over the telescope for a week at a time, This is, I told you about this project back in 2020. We'd gotten 1 year of data. We got delayed by a year. We call the project mishaps. It's just an acronym. We got delayed by the pandemic. We got some data in 2021, and then the schedule got screwed up and we didn't get our last year of data. So we've only just got our last year of data last month. And so we've now got all the data we need for this bulge planet search. We're going to be monitoring roughly 2 million stars that are of the right brightness and size, and we expect to find about 100 planets from there. And because we had those delays, we also needed to kind of, as a side project, we decided to do something that we could do more quickly, and we observed 2 globular clusters using basically the same technique to search for planets in the globular clusters as well. And so what we're using is the transit technique. We're watching for the planet to pass in front of its star, and that's most sensitive to nearby stars that are planets that are close to their stars. The closer the planet is to the star, the more quickly it goes around, the more times it repeats, and the higher the probability it actually passes in front of the star from our perspective. And so that allows us, if we measure the brightness of the star precisely enough to detect the presence of the planet. We have to be very precise though, because even a planet as large as Jupiter, which is about 10% of the radius of the sun, it's not the radius, it's the area that matters for the amount of light that goes missing when the planet passes in front. And so 10% squared is 1%. And so we need to get very precise measurements to detect that small 1% change in the brightness of the star. And that's why we need this 4-meter telescope to do this in kind of the distant center of the galaxy. But we're doing it, it's working. So this is data that we gathered of a candidate. I believe this is a candidate. It may be a signal injection, but I have candidates later if this is one of the fake ones that we put to test our sensitivity. And so you can see that we can clearly see this signal. And so we're working through a bunch of these candidates now, more than we've had at the time with just 1 year of data. I say year, it's only 1 week at a time from a year. So yeah, we have more data. We've got these candidates where we see multiple of these transits. And so we're making good progress with that. And we're also making good progress with the globular cluster data as well, which is actually our main priority at the moment, because we've got a better data, a complete data set more quickly. So
I have a question.
Yes.
About monitoring a planet while watching it traverse in front of the star.
yes.
How many of stars out there are the planets in such a plane that they're looking at, that they're perpendicular, their plane is what, in our
Yes.
eyesight, so to speak?
So that depends on how far away the planet is from the star. So the closer the planet is to the star, the more likely that plane intersects the
Viewing angle or whatever you want to call
So
it.
yeah, so if my hand is the star
Yeah.
and the planet is close, it can have quite a wide range of angles and you still see it pass in front. But if it's out here, it has to be a very precise
Okay, gotcha.
angle. So yeah, that's why another reason why we search for these hot Jupiters close in is because there's more of them actually transit in. So I think it's a 10% chance for a hot Jupiter. So like with a period of 3 days or so. For Earth, it's about 1%. I think. Yeah. So yeah, this is the process of the planet orbiting the star, and that's so that's exactly what we're looking at.
Yeah, so you can't actually see the planet, you can only see the change
That's right.
in the light.
Yes. Yeah. So the planet, the planets when they're this close, they are hot enough to emit sunlight, but very little compared to the star. So yeah, another reason why you should be careful what you name your survey. This was the first observing run. Turns out I had a gallstone, and gallstones present in a similar way to an artifact. So the medical staff on the mountain got very concerned in this kind of region. And, so yeah, I had to go down off the mountain for a night while they checked me out on monitors. Thankfully, I had an observing partner there to take this picture, and more importantly, take pictures of keep the telescope operating. But thankfully, the next night we were able to see a transit of a body in front of a star. This time, though, it was the moon in front of an eclipse of a solar eclipse, basically a total solar eclipse. Thankfully, I got back up on that in time to see it. Here again is my observing partner. But also not following advice.
Yeah, it's kind of looking at it with no protection.
To be fair, it was very low on the horizon, so it wasn't too bad. But
Most of the infrared still gets through.
yeah. But yes.
Whose bulge, that was the Milky Way?
Yes. So yeah, this is the Milky Way galaxy. Sorry, I tend to just say the galaxy when I say
No,
galaxy.
I might have missed it. Okay.
So yeah, that's our survey. Here is an actual candidate. This, though, is not actually a planet. It's a pesky binary star next to it. So we built up a lot of the tools that we need to distinguish between kind of eclipsing binary stars that have a very similar signal. This is where it was. It just happened to be close enough to cause a signal in the nearby star. We've kind of been building up these tools, and we're really ready to start cranking out the candidates and making the occurrence measurements, but we're not quite there yet. We've also been using the data in the meantime for other fun projects, like looking for asteroids that show up terribly on this monitor, but we're observing the same patch of sky regularly every few minutes. And so asteroids, perhaps they move pretty quickly across the field of view. And so if we stack together, make color images of the difference images, so we subtract one image from the rest, that removes all the dense star field that you saw in the image a second ago, and leaves just things that change. And asteroids basically they're changing position, not changing brightness, so we see those as well. We submitted hundreds of measurements to the Minor Planet Center. 4 of those have resulted in kind of new asteroid designations, so not discoveries, because that process is very complicated and requires the asteroid to be observed over several orbits, which takes a long time. But yeah, we've got new designations for 4, and then there's still a bunch of them that are just kind of isolated tracklets that no one's seen before, but we did get a long enough sample of the orbit to declare it a real object here. So we modified our observing strategy to observe fields slightly around our field as well once a night to increase the number of asteroids that actually comes out. Okay.
What scheme do you use for your absorber sign designation?
Sorry.
What scheme do you use for your absorber assign designation when submitting new measurements of minor planet stars? What scheme do you use?
I don't know.
I know when you
That's Stephen's big thing is
submit
asteroids.
your absorber assign designations to minor planet stars.
So we submit all of them as if they were a discovery.
I know you, but
Yeah.
what do you use for that designation?
Oh, we just use a pair of letters indicating
What
who
letters do you
Sorry?
use? What letters do you use?
reference.
Letters do you use?
I'm sorry, I'm not following.
What letters do you use?
Oh, letters. So it depends on who made the measurement in the images. So most of these were done by an LSU undergrad, Mars Newman, so they're MN,
And then,
and then we have a number after that.
of course, because I have done that when I use S and T for my, when I do new discovery.
Yeah.
New things, and not really discovery anybody I use.
Yeah.
No, I use its standard designation.
So yeah, we just track the ones that we just designate them by who made them.
I think generally speaking, they like you do. Some cases they like you to assume everything is new.
Well, so we're very, very faint, so most of the stuff that we find is, and then they have automatic processes
Yes.
to find.
I have done things before.
We should talk more about it.
No, I will.
So the last thing I want to say about the survey is that we are starting to put our data into the Zooniverse, so other people can look through it. And we're still at the early stages of this, but this is the kind of thing you would see. So this is all our data every night, and then we flag things that we think are transits, and then we'll be asking for the public. You may need to basically click on the ones you agree with our automated search. This may be real, but a lot of the stuff we find is crap, and so we need help to sort through it. We do that visually ourselves, but you get a better result if more eyes are. So I will stop there because over time, and so that's the progress we made on this project.
So aside iron and ox, are there any other competing ideas?
So the reason why I'm using oxygen, I'm not actually looking for oxygen specifically, but generally, so first thing that astronomers measure when they try and categorize how much other materials, so not hydrogen and helium they have, is they classify it by ion metallurgy. And so they're not very accurate in what they're actually measuring. They're usually inferring iron from some other measurement, but they report iron typically. And then if they're going to report some other difference from iron, they report alpha elements. And so these are elements that have increasing pairs of 2 protons. So oxygen, carbon and nitrogen are actually alpha elements as well. But yeah, they're all grouped together into alpha elements. And so that's where the mishaps names come from. The A here is alpha. And so we're looking at high alpha populations. We don't have to distinguish between the different elements. Beyond that, you need to do spectroscopy. We're looking at very faint stars, which are just, much.
Any other questions?
I just want to confirm this before I go spread this in my family. And I guess I've never even thought of it like this. Depending on the origin and the type of star, collision or explosion.
Yeah.
Wherever that solar system with their exoplanets, their ratio of elements can be very different than our ratio of elements.
Yes.
So that would make why the exoplanets are so different.
It could be. So we
Could
don't
be.
know at this
don't-
stage. Where
okay.
That's the thing that we're trying to find out.
Okay.
So yeah, I think that, so we typically measure iron, and so the planet metallicity correlations are based on iron abundance. And so they predict some number of giant planets per star in, say, the galactic bulge, the center of the galaxy. I'm saying that you probably have to look at the amount of oxygen, not the amount of iron. So we should find more planets with our search than you would predict from the iron abundance of the galactic center. But that's a hypothesis we're trying to test. We're going and measuring how many we see.
But am I correct to say there could be a solar system? I guess because my husband and I just keep, is there life? Well, so their solar systems, their ratio could be totally different.
Yeah.
Is totally different than ours.
Yeah.
Okay. Oh,
So,
so
yeah,
it's all about where they came from the recycling.
Right.
Pot.
Yeah. So there's a concept of the galactic habitable zone,
Right.
and so this is I don't know the full details of it. I don't tend to life is beyond where I'm thinking at the moment, so I don't think too carefully about this, but basically in the center of the galaxy, if it formed quickly, it might not have had time to build up those kind of selenium, those weird elements that are necessary for at least human life and probably plant life as well. So maybe there's no life there because, again, there's no.
But I'm talking about, am I correct, where the nebula
Yeah.
that our solar system came from and this other solar system came from?
Yeah.
The nebula ratios
Yeah.
could be totally different.
Yes, that's correct.
That's what I wanted to be clear on.
Yes.
That's a total different thought than I've ever had.
Yeah.
No, I'm so excited right now.
I had one quick question, but
Yes.
is to a small degree there tied in that? Another. I've been reading that the JWST and some of the figures from some of the earlier stuff, they're finding fully formed large galaxies that are only about 500 million years old.
Yeah.
And they're saying, by what we know right now, they can't form that big in 500 million years. It takes a billion years or more. So now they're saying, we're gonna probably have to revise all of our thinking on the origins and stuff, because we've got these huge galaxies that are formed that we can see pictures of, that by everything we know, it can't happen.
Yeah.
So do you have anything to say on that?
So my impression is that these headlines are slightly overblown. It's probably not going to completely overturn how we think about how things form, but the observations are straining the current understanding. So, yes, the current understanding or the past understanding was that you need a certain amount of time to form these galaxies, and the observations are showing they exist before that. But you probably only need tweaks around the edges of the theories, not a complete overhaul.
But anyway, I just want to ask your opinion. Okay, well, I want to thank you very much, Dr. Finn.
No problem.
Got any of the live streaming stuff?
You can say goodnight and we'll close it out. Just
Well, we only have a